Ahoy there, mateys! Ye come seeking adventure and buried treasure, eh? Well, ye hearties have come to the right ship.
What? Hey, get out of here! These animatronic pirates always trying to blow up my spot. Anyways, I think what he was trying to say is, you're about to embark on one of the newest rides at Sketchyland. Pyruvates of the Caribbean. Yeah, Pyruvates. But don't worry, even though the purpose of the next two videos are to cover, in gory detail, glycolysis, there will still be buccaneers and scallywags and scuttles and everything you've come to love about those filthy freebooters of the sea. Why do we need to know about glycolysis? Well, the end product of glycolysis is pyruvate, a 3-carbon molecule that feeds into a number of important pathways depending on energy needs and whether oxygen is present. Please check out our Fates of Pyruvate sketch to learn more. Anyway, the whole point of glycolysis is to break down 1 glucose into 2 pyruvate, 2 ATP, and 2 NADH. As a reminder, ATP serves as energy for cells, and NADH, or nicotinamide adenine dinucleotide, carries high-energy electrons used to make ATP via the electron transport chain and oxidative phosphorylation. Take a look at the schematic of glycolysis here. The glycolytic intermediates and enzymes in this diagram will directly match the character order in our sketch. Looking at this daunting diagram, you may feel dead inside now, but no worries. We'll break it all down step by step. Before we start the ride, turn your attention to that central island. The whole island represents the net equation for glycolysis. Get it? Because there's a net. To the left of that suspiciously arrow-shaped shovel, you'll see 1 glucose candy treasure chest, 2 powered-down ADP robo-seagulls, and 2 empty NAD+ bottles. To the right of the shovel arrow are 2 pyruvate pirates, 2 ATP-powered robo-seagulls, 2 full NADH energy drinks, 2 water canteens, and 2 H+ binoculars. These symbols are going to come up throughout our glycolysis duology, so keep your eyes peeled for them. Glycolysis occurs in the cytosol, and to help you remember, we've included a cast member pouring cytosol gel into the water to disinfect it because, let's be real, the water is probably nasty. Glucose crosses the cell membrane via GLUT membrane proteins. Our 6-buttoned robot pirate here with his foot on this treasure chest represents glucose. From here on out, any pirate with 6 buttons signifies a 6-carbon molecule. 6 buttons, 6 carbons. Just like 6-carbon glucose. Also notice he's got a gnarly 6 hook. That's to mark carbon number 6. If you look real close, you'll notice the battery slot right beneath. This is going to be important in the very next step, but for now just keep in mind that this glucose pirate's hook arm has an empty battery slot. In order to keep glucose inside the cell and initiate glycolysis, it must be trapped first. In step 1, hexokinase uses ATP to phosphorylate glucose to make glucose 6-phosphate, better known as G6P. You'll see a kind hex wrench worker kindly taking a phosphate battery from his ATP battery pack and adding it to the 6-hook arm of the glucose pirate to make G6P. He's wearing a kind button to remind you that he's a kinase, which transfers phosphate groups from ATP to substrates. We'll be using kind buttons to represent all kinase characters. We've included a waterfall to show that this step is irreversible. You might see this enzyme referred to as glucokinase, which is found in the liver and pancreas. Glucokinase serves as a hormone-dependent sensor for glucose metabolism. We'll talk more about the differences between hexokinase and glucokinase in the glycogen synthesis sketch. G6P is trapped inside cells because the phosphate group makes it negatively charged, so it can't cross cell membranes. G6P is an allosteric inhibitor of hexokinase, meaning that it binds to a part of the enzyme that's not a part of the active site. This disrupts the active site and temporarily deactivates the enzyme. G6P binding to hexokinase is like changing your apartment locks to get away from your crazy ex-boyfriend. A pretty effective inhibitor. Or in the case of our pirate friends here, assaulting the worker is a pretty effective way to stop him from adding phosphate batteries to any more glucose pirate robots. Next, phosphoglucose isomerase turns G6P into fructose 6-phosphate, aka F6P. Our iced-up isomerase worker here is rearranging 6 wires on the inside of our hook-handed sea hero to get him ready for his fruit feast. Much like how phosphoglucose isomerase rearranges the 6 carbons of G6P into F6P. And on that note, say ahoy to our F6P pirate. She's holding fruit to remind you of fructose, and the filled battery slot next to her 6 hook shows the location of the phosphate on the 6th carbon. In step 3, phosphofructokinase 1, or PFK1, kindly transfers a phosphate group from ATP onto F6P to make fructose 1,6-bisphosphate, aka F16BP. PFK1 is represented by another kind button-wearing cast member adding a phosphate battery to the one peg leg of the 6 hook-handed pirate. Yep, that's right. The peg legs represent carbon number 1. Oh, by the way, he's surrounded by fruit to remind you of phosphofructokinase 1. This step is also irreversible, as shown by the waterfall. The 6-hook pirate now has 2 phosphate batteries, one in his 6-hook arm and one in his 1 peg leg, hence F16BP. So far, we've used 2 ATP. Step 3 is a key rate-determining step in glycolysis. Let's mention how PFK1 is regulated. First off, ATP and citrate are allosteric inhibitors of PFK1. ATP, a product of glycolysis, provides negative feedback into the pathway at this point. Think about it. If we have enough ATP already, why would we want to make pyruvate and NADH that ultimately result in a lot of ATP? Therefore, when ATP levels are high, it inhibits PFK1 and slows glycolysis until the ATP supply decreases. And you know what's a great inhibitor of putting a P battery in the 1 peg leg of this F6P pirate? One very angry ATP robo-seagull attacking with citrus fruit. Oof, right in the noggin. And speaking of citrus, onto citrate. Citrate is a TCA cycle intermediate and the other inhibitor of PFK1. And spoiler alert, our end product of glycolysis, pyruvate, is eventually converted to citrate during the TCA cycle. When citrate levels are high, that means the intermediates of the TCA cycle are saturated and we can slow down glycolysis. Citrate leaks out into the cytosol to inhibit PFK1. Just like how this orange falling on our friendly cast member distracts him from doing his job. Alright, we've slowed it down, but what about revving up PFK1? AMP, ADP, and fructose 2,6-bisphosphate are all allosteric activators. AMP and ADP are byproducts of ATP metabolism. High AMP and ADP levels means that cells don't have enough energy and have used up most of the ATP. Therefore, AMP and ADP will activate PFK1 to stimulate glycolysis and make ATP. Just like how our PFK1 cast member is getting pumped up from the music coming from the amp right next to that ADP battery pack in 2,6 fruit. Wait, 2,6 fruit? Yep, like I said before, PFK1 is activated by fructose 2,6-bisphosphate, or F26BP, which is produced by a separate enzyme called PFK2. We'll explain why when we talk about gluconeogenesis. Up until this point, we've dealt with a single 6-carbon molecule of either the glucose or fructose variety, but that's about to change. So here we are. We have this innocent molecule of F16BP that's effectively split in half. Big Al here is demonstrating the proper technique used to separate the top half from the bottom half of our F16BP pirate. Aw, Aldolase would be so proud. As a result, 2 3-carbon molecules are born. The first we're going to talk about is glyceraldehyde 3-phosphate. Just kidding, it's called glyceraldehyde 3-phosphate, or G3P, as shown by this climbing pirate with his phosphate-powered 3 ice pick arm. Yep, that means there's a phosphate on carbon 3 of G3P. Also, take note of what he's scaling. That's a glacier to emphasize glyceraldehyde. Glyceraldehyde. Well, if G3P is the poster child, dihydroxyacetone phosphate, or DHAP, is the not poster child. But we're still depicting it here as a nice and useful treasure scale, and it looks just like DHAP. And don't even think about touching it. Please. Do we just throw away poor DHAP? No, that's a waste of energy. We'll give it a makeover in step 5. While G3P is all ready to move on to the payoff phase, DHAP needs a little extra love and attention. Triose phosphate isomerase, or TPI, comes to the rescue. TPI isomerizes DHAP into G3P, just like this cast member rearranging some wires in our DHAP treasure scale. Sounds painful. We'll spare you all the gory details. Alright, let's quickly summarize. Glycolysis produces 2-pyruvate, 2-NADH, and 2-ATP from 1-glucose. Glycolysis occurs in the cytosol. First, hexokinase irreversibly uses ATP to phosphorylate and trap glucose inside the cell to make G6P. G6P inhibits hexokinase via product inhibition. Next, phosphoglucose isomerase turns G6P into F6P. Then PFK1 turns F6P into F16BP by using an ATP to add a phosphate group to F6P. This step is irreversible and highly regulated. ATP and citrate inhibit PFK1, while AMP, ADP, and F26BP activate it. Afterward, aldolase cuts F16BP in half to make G3P and DHAP. Finally, triose phosphate isomerase turns DHAP into another G3P. So we're left with 2 G3P molecules. And remember that so far we invested 2 ATP. And that brings us to the end of part 1 of glycolysis. Stay tuned for part 2 in the next video.